Hello students, today we continue the point reflection of waves. In the last lecture, we have studied reflection of transverse waves from denser medium as well as from rarer medium. Today we will discuss the reflection of longitudinal waves from denser medium. In the first point, we discuss reflection of longitudinal waves from denser medium. And you know that we always take the denser medium as a rigid wall. Here also we take, in the first diagram, we take here there is a rigid wall which is here. This vertical line is the interface between denser medium and rarer medium. Wave is propagating from rarer medium on this interface. So wave we have to show here in this way. This is the rarefaction. You know, rarefaction is the region where the particles of the medium are separated, widely separated, and pressure is low. And near the wall, as the wave propagates, near the wall there is compression. In compression, particles are closely crowded and they are having that region is having high pressure. This high pressure zone or high pressure region, and wave direction of propagation of wave is shown like this. Also, there is one property of this longitudinal waves, that in the central part of this or central point of this compression, we can show the particle velocity. Here it is denoted by Vp, and wave velocity can be denoted by V. In case of rarefaction, particle velocity is opposite to the direction of wave velocity. Here, when compression is incident on the rigid wall, it exerts pressure or force on the rigid wall. Wall is not free to vibrate, therefore it exerts an equal and opposite reaction on the compression or particles, and therefore we observe that when the wave is reflected in the same medium, this compression also reflected back, and the particles velocity can be shown like this. Here this is Vp. You also can remember that when compression pulse is incident on denser medium, it is reflected back as compression. Now, when on the rigid wall, if rarefaction is incident, this is the second diagram. This is Vp, this one is Vp for rarefaction, and direction of propagation in this case we show like this in the second diagram. This is the reflection in the first diagram. This one is direction of incident or direction of propagation of wave. Rarefaction pulse is incident on rigid wall. Then we know that it is low pressure region. It does not exert any force on rigid wall. Wall also does not exert any force of reaction, but the energy is reflected back in the same medium or comes back in the same medium, so that here the rarefaction changes its particle velocity. The compression also changes its particle velocity, and we observe that rarefaction is reflected as rarefaction. We can write here the points. Reflection of longitudinal waves from denser medium. We can write here wave velocity is reversed, because it is the property of any progressive wave that when it is incident on the interface of denser rarer or rarer denser medium, it has tendency to go back into the same medium. Therefore, wave velocity is reversed here. Wave velocity we write as V. Similarly, particle velocity Vp is reversed. Particle velocity, here we know that all particles are vibrating, and for the vibrational motion the velocity is given by V is equal to omega under root a square minus x square, like this. So this is the point we have revised in or studied in oscillatory motion. So the particle velocity can be given by this expression. Now we write compression is reflected as compression and rarefaction is reflected as rarefaction. You can note the points here. In short, we have written these points and the diagrams. So you have to remember these points. Reflection of compression as compression, reflection of rarefaction as rarefaction, and these points you have to remember in case of reflection of longitudinal waves from the denser medium. So note these points, and then we continue the point of reflection of longitudinal waves from the denser medium, in the rarer medium. Rarer medium. So for that we consider the boundary, separating here by the dotted line, and same case we discuss here by considering the reflection. So here the boundary is there. Here there is rarer medium, and comparatively here there is a denser medium, and the same longitudinal wave we take here, that is compression pulse. Here compression pulse is incident, this is Vp. Here Vp is like this. This is direction of propagation denoted by V. The same explanation is here. The compression is the region of high pressure. Particles are crowded. They exert force on the boundary. Here the boundary is not rigid. Particles are loosely bound, they are loose there, so that this compression can exert a force on this, and the boundary can be shown like this. Compression means the particles in compression push the boundary. Here there is pushing the boundary, and we observe the rarefaction is reflected back into the medium. So instead of showing it, we show like this. This is wave velocity. But in the explanation we have to say it that rarefaction is, here compression is moved further and rarefaction is reflected back. So this is the wave velocity, particle velocity, this is the wave velocity. Now in the second case, if the rarefaction is incident, this is the particle velocity, this is the velocity of wave, means wave velocity. The particle velocity, in case of rarefaction it is opposite. Here it does not exert any force on this rarer medium, therefore the rarer medium boundary also does not exert any force of reaction, but the particles go inside the medium, and we observe here when the wave reflects back, it is in the form of a compression. Here rarefaction is reflected as compression. We note the point when reflection of longitudinal wave from rarer medium, we note the point wave velocity is reversed. Particle velocity is also reversed. Particle velocity is not reversed, Compression is reflected as rarefaction. And you can write vice versa. Rarefaction is reflected as compression. So this is the discussion about the reflection of longitudinal waves from the rarer medium. So you have to note these points and draw the diagrams showing the wave velocity as well as particle velocity. So these points you can, if you study such discussion, then you can solve the multiple choice question as well as very short answer questions. So today we'll stop here. Thank you.